Okay, so Markov chain has transition matrices. A transition matrix is a matrix in which probability of going from state A to B is given to you. So this is going from S to S. This will remain in S. This is going from S to R. Correct? So basically, if they ask you to draw in the transition diagram, so basically S to S is 0.8. S to R, you interpret like this, huh? S to R. Correct? Sorry. R to S. Oh, it's going like this. R to S. S to S. S to R.
Oh, it goes from up to down.
It goes from up to down. And you know, when we're doing graph theory, it's going this way.
When graph theory goes this way.
Yeah. Graph theory, we went it this way. You remember in some of the matrix?
Yeah.
But then this is going from this to this. This to this. Anyway, this will add up to 1. This will add up to 1. Look.
Okay.
So if the columns add up to 1, basically it's going from this to this. You remember that. If the rows add up to 1, it will go from this to this.
Of the rows add to 1 it goes from?
Yeah. The directed edge from S to R.
If the columns
S to R is 0.2. Yeah, S to R is
so
0.2.
if the columns add to thing, then it's
1. If the columns add up to 1, then it's going like this. Okay. Now, for a system, find a probability that sunny days, so this is sunny and rainy, correct?
Yeah.
Correct? 3 days later. So if you want 3 days later, you do it 3 days later basically. Correct? So you raise it to 3. So 3 days later, they want probability of the rainy today. So probably rainy today. Find a probability it is sunny 3 days later, given that it's rainy today. So it's given that it's rainy today. So this is R2 sunny, like this.
Wait, so given that it's rainy today, so R dash.
So you start with this today and after 3 days. Today and after 3 days. So rainy after 3 days will be this. Initial state probability vectors. We can also take the initial state.
Yeah,
0, 1.
Steady state. Huh?
Yeah.
Is it always 0, 1?
0, 1 because because if it's sunny, rainy this way, then this will be sunny, rainy this way. Okay. Now if it's rainy today, means you put 1 over here. Actually, if it's sunny today, then you put 1, 0. You see, like this is there, this is not there. Present, absent. Yeah. So present is 1, absent is 0, basically. It's like your logical circuits. So then you multiply. So this is probably sunny. So remember the rows with columns. So if this is sunny, rainy, this will be sunny, rainy like this. So that for a transition matrix T, an initial state S0. This is the initial state. So state will be no, initial state. So initial state will be always be 0, 1 or 1, 0, depending on.
Steady state.
Steady state is after how many trials it remains the same.
Oh, between 99.
The probability remains the same. You know, this and this and now again you will multiply this by 4, this will change.
Yeah.
But sometimes what will happen when you do 6, 7, 8, this remains the same.
Then
there's no change in this.
They ask like at what value when this becomes
steady state. So this is a state after n transitions, n time periods. Calculating the long state and the steady state and long term probabilities. So you take a large number basically.
Like 50.
50, 100. You take a large number and see when this doesn't change substantially. Yeah. So this becomes a steady state. You take large powers basically. Correct? There's another method of doing it. This is method 1, taking a large power.
Will they ever ask?
The other method to find the exact value, they'll ask you the exact value sometimes. To find it, because exact value, this will give you in decimals. If you want exact value, then you do TS is equal to S and solve. We'll see that. It will come in some example.
So for TS, you do S into T inverse. T inverse in the S.
Yeah. That will come to that. This is a transition matrices are easy. These are easy. Correct? 18th. See, for the example, use the method demonstrate find the exact steady state probability. So then you have to do Ts is equal to S.
So you get like four
So
families.
Ts, yeah, you get 4 families, you get 4 equations. 1, 2, 3, 4, and also this is important that a plus b plus c plus d is equal to
So
1.
we call it probabilities.
Yeah. And you solve it simultaneously.
But you already have four equations. So then why do you have to include a plus b plus c plus d as well?
There are 4 equations. Yeah, then it's not required.
You don't need it.
Yeah, then you don't need it. Then no, you'll use it here to find d.
No, but if you do.
There are 5, no? A, B, C, D, and there's a constant. Achha, anyway, A, B, C. So four, but you'll get in terms of D. You'll get infinite solutions.
Really?
Yeah. You'll get in terms of D. You won't get a numerical value.
Can I try?
Yeah, try. You won't get a numerical value. You put it back in this and get the value of D, and you'll get A, B, C, D.
Okay, let me see. How many 4 unknowns?
Yeah.
So minus.
So if you put your calculator, you will get like this. T you will get. So T is like your D, you can call it. And then you put in that and you will get. So that will give you the exact values. Now further going down in the transition matrix, this is also important. A gambler takes $20 in casino to play roulette. He places $10 on red each time.
Yeah.
If it lands on red, he wins $10. If it lands on black, he loses $10. He continues to play until he either loses his money or reaches $30. So let's see. So basically,
the probabilities of getting red and black are both 0.5.
Yeah. So now he starts. So what happens if it's 0?
1.
Why?
Because either you either win 10 or lose 10.
Yeah. Places red. If a ball lands on red, correct, he wins $10. If it lands on black, he loses $10.
It's like 50% of winning and 50% of losing.
Losing. He continues to play until he loses all his money or reaches $30. Assuming the probability of getting red or black is each this, set up a transition matrix between $0, $10, $20. So $0 anyways, he'll stay at $0. He doesn't have money to play over it.
Until he loses all his money.
Yeah, he lost all his money.
30 will be 1.
If he has $10, then
he's half a chance.
Why? Because if it's $10, either he'll get either will become 0 or he'll become 20.
Oh yeah, it's going this way. Yeah.
Either become 0 or he'll become 20.
Oh, it's going this way, no?
It's this way.
10 to 0.
So if it's 0, he remains 0 only.
Yeah.
If it's 10, then either he'll become 0 or he'll become 20. Achha, if it's $20, then he'll lose $10 to become 10.
Yeah, and
or he can gain 30.
Gain 10 30.
Now if he has 30, he remains at 30. He doesn't play. So that's your transition matrix. This was a tough sum. And then, okay, find the probability that he ends up leaving $30. So you find out the steady state. Correct? So what is the probability that he ends up with $30? He ends up with $30 from anywhere. 20, 30, why is this I've taken? I don't remember that.
Why is?
Probably that he ends with $30 is from probably from the 20 to 30. Yeah.
Assuming the probability is going to.
When will he reach 30? Only from 20 to 30.
20, yeah.
So you see from 20 to 30. Tough sum this was.
But I mean,
diagonalization of a matrix.
You define
any matrix M has two distinct eigenvalues, lambda 1 and lambda 2.
Yeah.
Can be expressed as M, the matrix M is P inverse.
Yeah.
Correct? Where P is a matrix whose column are eigenvectors. So eigenvector 1, vector 2, P is that. D is what?
Eigenvalue 1, eigenvalue 2.
Eigenvalue 1, eigenvalue 2. And P inverse is the inverse of this matrix, which is formed by the vectors.
Yeah.
Diagonalization matrix.
The eigenvalues you just do like the value minus lambda equals 0.
Correct. Now see, listen, you have to do it on calculator, but you have to remember, and this is then your formula book. Once you know the eigenvalues and eigenvectors of matrix M, you can find matrix P and D such that M is equal to P, D, P inverse, where D is a diagonal matrix. That is matrix of this form. And this process is known as diagonalization. Now, where is this useful? See, like this. We'll so use of diagonalization here. Here's some here. See. Order, yeah, this one. See.
They've already given the eigenvalue.
Yeah. This is just okay. What is the use of that formula? So matrix M has eigenvectors 1, 3, 1, 1, and eigenvalues is this. Find two possible values of M1 and M2. So now the first possibility is what? Whatever eigenvectors you have, you put that. Correct? You put that. That's your P.
And in the second, you swap the taking switch the thing around.
Now here, this is your 1, 2. So you take 1 and 1, 0 and 0 minus 2. And this is the inverse of this.
Yeah. So
you do this in the calculator.
Yeah. And the next one you do 1, 1, 1, 3, then 1.
1, 1, 1, 3. This you keep it as it is. Don't change this also. Don't swap this also. And the inverse of this, and that's this.
No, but then won't the eigenvalue correspond to the eigenvectors?
No, they don't.
They don't?
They should ideally.
Yeah.
But these are the two possibilities.
Okay, fine.
Because they haven't given you which corresponds to which.
Oh, yeah. Okay.
In this sum, they haven't given you which corresponds to which. If it corresponds to this, then for this, you have to take this correspondingly. You know that, huh? For V1, you have to take lambda 1.
Yeah, and for 1, 1,
for V2, you take lambda 2. But here they haven't given you which corresponds to which.
Corresponds to each other, you just do minus 2 or 0.
Correct. So that is important. It should correspond. So this is, you know that, no? Transformation using matrices.
Yeah, that formula booklet.
That formula booklet you just apply. Please go through all this. Huh? There's a lot of things there.
Yeah, matrices a lot.
Yeah, see, A raised to 60. Now this is very, 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 very important. Exactly they want. So you can't use a calculator. So now listen, what are the steps? First you find the eigenvalue and the eigenvectors. Correct? So to find out the eigenvalues, you take the determinant A minus lambda I is equal to 0. Correct?
Yeah.
Your determinant, you do this, determinant is this and this. Use your calculator, get your lambda 1, lambda 2. Now once you get lambda 1, lambda 2, what you need to do is you need to find a value. You remember how to get this? Minus x plus y. Yeah, this is you basically you take your xy. What is happening is, if you're getting, how do you get this equation? So what you're doing here is, you're writing this, correct, into this,
into xy
is equal to lambda times xy. So if you take the first equation, this will become minus x.
And you take minus lambda.
So say this one. Yeah. Correct? And then you cross multiply. And you find x upon y. So your this is your x and this is your y, because we are looking at a vector.
Then what if you do the other one as well?
You'll get the same answer. If you do the other one, no?
No, I'm saying if you do with root 3 also, no?
Yeah, with root 3 also. No, that is here. That's done here.
Huh.
I can't show you both together. No? I have to show you one at a time. Okay. Now what do you do? So these are my vector v1, this is my vector v2. Now you set this up.
0, 1, 1, 1.
This is the main formula basically. This is what we are using it for. The diagonalization is used for this. So a raised to 60 is p, d 60, p raised to minus 1. What is your p?
1, 1, 2, 3.
P is with the vectors. This v1, v2.
Then the eigenvalues also.
Now for this corresponds to minus root 3, no?
Yeah.
Correct? This corresponds to minus root 3. So this, if you put this first, this should come first. This you put second, this should come second. And this. Now we have to do by hand. Now there's a rule which says that this will obviously common sense indices.
Yeah. becomes positive.
You find the inverse of this using calculator. Correct?
You take the denominator out.
Correct? And this you take this in front. Huh? Now what will you do is, you will multiply this with this, rows by columns. So this into this plus this into this. Correct?
Yeah.
Then you take this row with this column.
Oh, so you did.
Then they take this row with this column. Put it here.
You take 1 upon 2, 3.
Then this with this.
Why do you take 1 upon 2, 3?
Because it's a constant, it's a scalar.
That's it's 1 upon determinant into.
That's in a formula booklet. No, this is directly calculated.
It's directly calculated?
Yeah, directly calculated. You can also do 1 upon AD minus BC.
Yeah.
And you interchange this, but use your calculator. Don't remember too many things.
No, when I tried it.
So, to find the inverse by hand, if your A is equal to A, B, C, D, then your A inverse will be 1 upon AD minus BC. AD minus BC, yeah. You interchange this and you change the sign of it. You change the sign of this. You interchanging this and you change the sign of these. You interchanging A and D. You interchanging the position of A and D.
Yeah.
And here you're only changing the sign of this.
Oh, and you make it through 3. Yeah.
You're changing the sign of this and this.
Yeah.
And you're interchanging, and this is your determinant. Yeah. Now you multiply this with this, you got this out.
Yeah.
Now this one, what will you do? You can remove 3 raised to 30 common. With each of them having 3 raised to 30.
Yeah, take that out of it.
And now you can use calculator to multiply this. It will give you this. Open the brackets, and this is your steady state. Now your calculator won't give you this. Raised to 30.
What?
Check. If you do this matrix raised to 60, it won't give you, no?
No,
there's another processing power.
Like go down. Like from that much will give you 3 raised to 30. From 3 upon 30.
3 raised to 30.
The last step.
Last step.
Like use the last step, no?
Calculator?
Yeah.
No.
It's 3 raised to 30 exact.
No, it doesn't.
It'll like something raised.
So in graph theory, the transition matrix, remember transition matrix, you have to enter the probability in the matrix. Remember?
Yeah.
That's the key thing. So this undirected graph shows tunnels a mouse can travel between junctions W, X, Y, Z. At each junction, mouse chooses his next tunnel at random. Okay. So construct a transition matrix T. So transition matrix, how will you construct? Tell me.
So are you going from T to, are you going from like Y, W to Y or Y to W now?
Both the ways you can go. No? This because it's not a directed graph. No? So from W, so let's start X. So this is X.
So X,
correct?
X
Y
is 0.
Correct. So this is
X.
So this is X.
W, X, Y, Z.
X.
What will be W, X, Y, Z?
Y. I don't know. I'm just writing it. X, Y, Z, W. Now what is the probability? It will go from X to X? Nothing.
Yeah.
Now Y to X.
Y to X, half.
Y half.
No, what will Y to X be? Y to X will just be 1, no?
How many roots are there from Y to X?
1.
So why is this half?
I think there's even I think even W, X, Y, Z.
W, X, Y, Z?
Yeah. Yeah, W, X, Y, Z.
W, X, Y, Z. W, X, Y, Z. Okay. So now check. So W to W, okay, nothing. And
W to X has 1.
X
to W is 1.2.
X to W is? Yeah, 1/2. No? There are two roots, no?
Yeah.
Okay. Y to W?
Y to W.
This is 1.
1.4.
1. Only 1, no?
Yeah, it's only 1. So why is it 4?
Okay. Now listen. So W to X. W to, first of all, from W, how many roots are there? How many roots are there from W?
So you take I
1, 2, 3, 4. There are 4 roots from W.
Yeah, okay.
There are 4 roots from W.
There are two from X.
Each will be 1/4.
Oh, yeah, okay, yeah, I got it.
Each will be 1/4.
Yeah, I got it.
The probability of each will be 1/4.
Yeah.
Now from W to X, they have 1/4 plus 1/4. So W to Y will be 1/4. Like that you have to do. W to Y.
So X to
W to
W.
Y would be 1/4.
So X to W will be 1.2, X to Y will be 1.4.
Correct. And W to Z would be 1/4 because you're taking one of these 4 roots that original. You have to interpret that way. Okay. Now let's say from X to W.
So it's not the probability of specific roots, the probability of the roots that
starts from there. So 1, 2, 3, 4. Each of this is 1/4.
Yeah.
So when you start from here, you have 1/4 chance of originating from here. Yeah. That's how you to interpret. Okay. Fine. The mouse is initially at junction this. Correct? Which junction is it likely to be after running 2 tunnels? So then what will you do? You know, do S naught T square. Now when they give you
not T square.
Because they're giving you in this row form.
So can you just like make it
you can
T square S naught when you make 0, 1, 0,
yeah,
0.
you can do that also. Same answer you get.
Yeah.
If you do that, but then you have to precede this.
Then you just get W actually.
Yeah, correct.
Same thing.
So yeah, so because otherwise you can't, if you're putting this in front, this should be row.
Yeah.
Or if you're putting this, you can put in column. Now different textbook use different notation. IB also making. So it will be open to that. By considering S naught Tn, so S naught T raised to N, T raised to some large power N.
Yeah.
For large values, show that in long term, each junction equally often. So you take a large value.
Yeah.
T raised to 50 and all that. And you will get this basically. Sorry. T raised to 100, you can get 0.25.
So all of the equal.
All of it.
So 1 second. No matter. Then
after 2 tunnels, you see the junction with the highest probability.
No matter which tunnel the mouse takes first,